Thanks for attending the Trilithic webinar series. My name is Tony Holmes, and I'm the Applications Engineering Manager for Trilithic. Today we're going to discuss digital troubleshooting. You'll also notice that there's a chat feature that's provided for you. Feel free to chat any questions to me, and all of the questions that are chatted will be responded to at the end of the presentation. Okay, let's go ahead. As a webinar outline, we're going to talk about the QAM basics. We'll talk about measurements. Different type of measurements using constellation, looking at constellation patterns, MER. We'll talk about BER. We'll talk about the FEC, EVM, and then we'll just talk about testing and noise measurement under QAM. I know you'll notice that that we use a lot of acronyms, but as we go through this, I'll actually explain what each one of those mean and what it's actually doing for you, and what types of tests that can be ran utilizing these particular things. Okay, let's dive right into it. Let's talk about the basics of QAM. So when we start talking about QAM, there's what's called decision boundaries when you're looking at constellation patterns. Each location on the constellation is framed by the decision boundaries. Sometimes they're called the decision thresholds. Now, whenever any bits fall outside of these particular boundaries, then anything outside the data that's there would be an error. So those are things that could not be corrected. If the bits fall within the decision boundaries, then those particular that particular data is received and it's able to be corrected. Now, the further that the bits start to, or the symbols spread out away from the what we call the ideal center of the decision boundaries, when they start to spread out, they get closer to the decision boundary, which puts you right on the edge of the forward error correction, not being able to make the corrections. And like I said, we'll kind of go into this in a little bit more detail a little bit later. Now, because the position on the constellation depends on both carrier amplitude and carrier phase, both the amplitude and phase noise will affect the location on the constellation. Amplitude noise will change the distance from the origin, and phase noise will change the rotational position. Other types of noise and interference can affect the symbols in all directions. So this kind of shows in this particular diagram how you see the symbol that's falling outside of the decision boundaries, or that's right on the edge. The one that's outside of there, that would be considered a symbol that would actually be lost, or that could not be interpreted, or would not be able to be interpreted properly by the forward error correction. But then you look on the left side where it's saying the signals within the decision boundaries, those that's in that tight cluster, or the cluster of dots in the center, those can be interpreted properly by the forward error correction. Now, by adding more levels to the I and Q channels, higher data rates can be carried. The higher the number of levels, the more effect there will be from noise or any other types of interference. Now, 64 QAM uses 8 levels in the I direction and 8 levels in the Q direction for a total of 8 squared, or 64 symbols. Now with 256 QAM, it uses 16 levels in the I direction and 16 levels in the Q direction for a total of 16 squared, or 256 symbols. Now this diagram shows the basic QAM forward data path. Now on the spectrum analyzer, the display will look like a haystack. And that's what the QAM carrier will look like for the downstream. Now, digital signals work well until very close to the point of failure. This makes measurement of digital carriers critical to determine the system margin. Signal level, MER, and BER are the vital measurements when you're checking digital signals. Now, the BER mode helps to find any of the BER problems. Now, many operators set 64 QAM signals 10 dB below the video, and for 256 QAM, signals are set at 6 dB down from your actual video carriers. Now, granted, the 256 QAM signal has a somewhat higher overall peak-to-average power ratio than 64 QAM, but it also needs a higher carrier-to-noise ratio to get the same BER as a 64 QAM signal, which is the reason that you have to have the 256 running a little bit higher to get it out of the noise floor in order to make that carrier-to-noise. Now, the other thing that's in your digital set-tops is what's called the adaptive equalizer. Now, the adaptive equalizer corrects the effects of reflections in the transmission path. The equalizer mode indicates the strength of specific reflections, their location in relations to the test point location, and it's going to show you how hard the equalizer is working to make those corrections. A primary function of this mode is to help the user maintain low levels of equalizer stress by locating excessive equalization at a specific QAM demodulator digital frequency or digital filter coefficients that require different corrections. Now, digital carriers can be very susceptible to reflections in the cable caused by really a variety of problems such as bad splitters, bad connectors, kinks in the cable, squirrel chews, backhoes, tree rubs, and so on. Reflections can cause errors in the signal because a reflection of a particular bit of data can overlap data bits that come later. Now, set-top converters have an adaptive equalizer that senses the amount of reflections and compensates for it. It's information to know how hard the adaptive equalizer is working to determine if there is any margin for system degradation. Now, the adaptive equalizer changes the level at a particular time. It's time-based. This time matches the time which the reflection occurs. The gain is reduced only at this time, thus reducing the reflection. So the thing is, even by looking at the drawing, you can see how it looks like a little stair step, and that's based off of the amplitude or the level of the reflection or signal that's reflecting back at that particular time interval, which you'll see that there's a footage on there as well, which since we can calculate what the timing is, and we can come up with what the approximate footage should be to that particular reflection spot. Now just remember, even though this is showing a footage, this is not designed to replace your TDRs. But what this is designed to do is to let you know how hard the adaptive equalizer has to work to make corrections, and it will also give you a general idea of where your reflections could be coming from. Okay, so now let's talk about just QAM measurements in general. So digital HFC services are distributed using a modulation system that transmits two data streams, each carrying its own independent information. Conventionally, these streams are called the I and Q. This is what we talked about earlier. Quadrature amplitude modulation, or QAM, is a means of modulating both streams onto one RF carrier. Now, the transmitted values of the I and Q occupy only a few predetermined, widely separated states. A modulation protocol, a set of rules, prescribes the number of allowed states for each type of modulation. For example, in a 16 QAM, the I and Q signals can have only 4 allowable states for each. In 64 QAM, each can have 8. So you can kind of understand what that's referring to. I and Q streams can be represented as being in quadrature, forming a grid that offers I time and Q possible states. The grid is conventionally referred to as constellation and may be thought of as kind of like an array of boxes, with each box representing a particular I or Q symbol state. The ideal or nominal location for a given symbol state is the center of the box. That's that tight cluster of dots that we've been talking about. The boundary between neighboring boxes, like what was mentioned, is the decision threshold. The MER, or the modulation error ratio, gives an indication of the digital quality, whereas the BER, which is the bit error rate, calculates the amount of received bits that had errors. And just remember, it's important to know if you are using true BER or estimated BER, which is the Reed-Solomon method. And I'll talk a little bit further about the differences between the two. So let's first talk about just reading the constellation diagrams, because we see it a lot of times, and and it's important that you understand what you're actually looking at. Like was mentioned, the boundary areas is called the decision thresholds or the decision boundaries. If a signal disturbance pushes a symbol across the threshold, it is incorrectly interpreted as belonging in the neighboring box, and then it becomes a bit error. Symbols that are not distributed enough to be pushed across the thresholds are always interpreted correctly. A constellation diagram is really a good troubleshooting aid, and it can give you clues concerning the source and nature of the particular disturbance. Now, reading the constellation diagrams, in a constellation diagram, all of the possible combinations of I and Q form a kind of a grid, making it easier to interpret and making different disturbances stand out. The constellation diagram can be thought of as an array of boxes, with each box representing one state of symbols. In perfect data transmission conditions, each received bit would land right in the center of its box, the nominal position for the particular symbol. But now in the real world, ingress reflections pushes the bit away from its nominal spot, or that ideal, cluster of dots in the center, toward the boundary of the adjacent boxes. If a signal disturbance pushes a symbol across that threshold, it is incorrectly interpreted, as what was mentioned earlier, as belonging to that neighboring box. So just remember that constellation pattern, when you're looking at that, the tight cluster of dots is what you want to achieve, like what you see in this particular illustration. Now there's what's called symbol rates. You'll see that when you look at looking at your digital meter or your digital analyzer, you'll see a symbol rate. The symbol rate corresponds to the size and shape, or the bandwidth, of the digital signal. Now the rate itself is expressed in millions of symbols per second. The default for 64 QAM, this is the NXB, is 5.056941. And then the default for 256 QAM is 5.360537. And those are just the default for the NXBs. Now 64 QAM has a total of 64 layers, or the decision boundary areas, the individual blocks, and 256 has 256 layers. And just remember, like I mentioned earlier, the more layers that you have, it increases the opportunity for interference. So some of the typical problems that you'll run into, or that you can see when you're looking at a constellation, is incoherent interference, coherent interference, and we'll talk about each of these, system noise, phase noise, gain compression, and IQ imbalance. So for coherent, as applied to light waves, is having an identical frequency and identical phase and traveling in the same direction. Lasers produce coherent light. So it's a distinct carrier that is transmitted. And some of these sources of coherent interference, can include like intermod products like CTB and things of that nature, PC clock harmonics, broadcast transmitters, whether that's like UHF channels, VHF channels, would be considered coherent interference. These types of interference displace the symbols in a given box into it's a telltale circular pattern. It kind of looks like a donut. So it looks like the cluster of dots with a hole in the center of it. And if the coherent interference is great enough, the plot of all the dots landing in the given box will form that ring, usually distorted by incidental noise. Now with incoherent interference, what that is that's more of random noise that kind of comes through the screen. And that's going to give the impression that the bits are pushed away, or kind of gives a cloud effect in the constellation pattern. Now, system noise is a type of incoherent interference. And this, if you look at the diagram here, you can see where the bits are pushed away from that ideal cluster of dots in the center of the decision boundaries. It's pushed away from there, and that could come from system noise, just noise in the system itself. Now there's also phase noise. Now phase noise, that's a term that's that's related to instabilities of an oscillator. This is a head-in type of issue that could come up. The oscillator is involved in processing of a signal as a local oscillator, for example. These instabilities are impressed on the signal itself. Now, the oscillators in signal processing devices are designed to add very little phase noise to the signals that they're handling. However, if you do have a defective modulator or a processor in the head end, it can add to phase noise, and it'll look like the actual constellation pattern is rotating. And then there's what's called gain compression. Gain compression is signal distortion caused by, it's usually caused by overdriving an active component like an amplifier or a processor in the signal path, or by defective active components. It's compressing the signal. In the resulting constellation, the corners are pulled in. It kind of looks like the constellation pattern is bowed. And that's when you see that type of pattern, that comes from gain compression. Then there's IQ imbalance. With IQ imbalance, the display will look taller than it does wide. These type of things come. This is going to be a head-in type thing that comes from baseband amplifiers, filters in the head-end, digital modulators, and so on. Now, looking at the constellation patterns that's on the screen here, you can look on the left side. That's what a good MER would look like. The tight cluster of dots in the center of the individual squares, or the individual decision boundaries. On the left, that's a poor MER. If you see that type of MER in the field, you have some work yet to do. So MER is the modulation error ratio. And this determines how much margin the system has before failure. Now, low MER is not noticeable on the subscriber's picture until the system failure. MER assigns a value to the fuzziness, or to that where the bits or the symbols are pushed out of that tight cluster of dots. The further the dots are from their ideal location, the worse that the MER is. MER is a figure of merit for the QAM signal that includes all types of impairments. So this kind of shows you what your picture quality is, and how how it can look good, and then all of a sudden it drops out. So if you look at the red lines that's going across, well, first of all, let's talk about the axis itself. When you're looking at the bottom axis that's going horizontal, that's talking about the signal quality. It's talking about the signal quality to getting to the point of a no picture. So, and then when you look at the axis going vertical, that's the actual the picture quality itself, how good the actual quality is. So if you look at the red, you're looking at it's going all the way perfect, and then all of a sudden, at the point where it goes to a no picture, you can see where it just drops all the way off. Versus your green, where that would be an analog carrier, to where you see that the carrier gradually degrades. And then that's what causes what we call a cliff effect. So what is a cliff effect? And I'm sure a lot of you have heard of that particular term before. So a cliff effect. Let's look at this particular illustration. That is a cliff. So if you look at it, if you had a blindfold on and if you walked towards the edge of that cliff, when you get to the edge of it, you'll fall off. That is a cliff effect. So here's a way of illustrating it. So if you look at this first display, there's a in that particular area there, we're working now in the operating margin. That's what we're considering good. But now this particular, we're rolling this up the hill and we're in the risk zone. That's the area that's close to failure. Now this is now running right at the edge, and that's the risk, or that's the actual the crash zone. So if you notice, in that particular area, it's now the causes the cliff effect. So you want to always keep your digitals working in the operating margin. When you start getting in the risk zone, you're close to the point of failure. And then once you're at a point of failure, all it takes is for a little hiccup, and you can be right into the crash zone. So hopefully that gives a little bit of a better illustration of what the cliff effect is. So now let's talk about BER. With each digital data transmission, some bits will, it's not going to be received, may not be received correctly. The bit error rate is the number of bits in error divided by the total number of bits in the data transmission. The ratio is expressed in scientific notation. So bit error rates are the bit error measures how often symbols are pushed into the neighboring symbol territories, causing these symbols to be misinterpreted. Remember I talked about earlier that whenever a bit falls outside of the decision boundaries, it cannot be interpreted properly. That's what adds to your bit errors. BER is expressed as the ratio of errored bits per some number of bits sent, and it's given as a power of 10. For example, a BER measurement of 3e minus 7 is 3 times 10 raised to the 7th power. Means that a given bit has a 3 in 10 million chance of being misinterpreted. So this kind of gives a better explanation or a description of your reading the bit error rates. The way that you want to remember bit errors is kind of look at the number to the far right side. So if you had like the 1e minus 0.6, that minus 6 lets you know how many zeros follow the 1. So you know in a million there are 6 zeros. So if I see that minus 6, I know that that means a million. So by looking at 1.0e minus 6, I know that that's one error in a million bits. If it was a minus 0.7 or a minus 7, that would be 10 million bits. If it was a minus 0.9, that would be a billion bits. So you kind of understand a little bit how the bit errors actually work, or how to read that number. On the left, the higher that the number is, the worse that it is, because one error in a billion bits is better than 2 errors in a billion bits. So a good signal, a 1-bit error per hour, or a BER 10 to the minus 10. True BER readings count all 10 billion bits for a BER reading of 10 to the minus 10. It's usually it's recommended that you wait at least 10 seconds to get an average before recording the BER reading. That's if you're using the approximate method or using the Reed-Solomon method. Now, when you're looking at it in as a true BER measurement, it takes approximately 23 to 25 seconds to look at a billion bits. So you need to at least look at it for that particular time so that you can base your readings off of a billion bits. So BER, like I said, a digital signal works well until very close to the point of failure. Measurements of digital carriers are critical to determine the system margin. Signal level, MER, and BER. Now the BER mode helps to find the problems itself. So you'll also see errored seconds. To get an idea of whether the errors are caused by noise or intermittent problems, if errors are received that can't be handled by the forward error correction and seen by the end user, this is known as errored seconds. If the errors in a 1 second period that the forward error correction cannot handle, these are considered severely errored seconds. So those will be considered like lost packets, packets that could not be interpreted properly, or those individual symbols that fell outside of the decision boundaries. In the BER mode, the errors are displayed as vertical lines. Errored seconds, and this is on the 860 DSPI, the errored seconds are correctable errors, and it shows up as gray individual vertical bars. If they're severely errored seconds, those are uncorrectable errors, which are solid black bars. Now, forward error correction, the FEC, can make corrections to the errors, but only to a certain point. Forward error correction adds redundant information to the data stream to decrease the number of bit errors introduced by the transmission channel. The BER before forward error correction is the sum of all bit errors, correctable and uncorrectable. BER after forward error correction indicates the number of uncorrectable errors the FEC was unable to correct. The difference between the pre and the post FEC, or the forward error correction, indicates how hard the forward error correction function is working and how close the system is to failure. Now, pre and post forward error correction measurements. QAM communication systems include the means to patch up some of the bits that become corrupted in a transmission. And that's what the forward error correction does. So forward error correction data included with the QAM data transmission is the information the QAM receiver uses, or your digital set-tops, to fix the misinterpreted bits. Now, because pre and post forward error correction data quality, it can differ greatly, BER measurements are typically specified as being either pre-FEC or post-FEC to indicate whether the data has already been repaired by the forward error correction. Pre-BER, or before the forward error correction, is the sum of all bits errors, and then post is after the corrections are made. And the way that this happens, or the way that what makes this works is in the data stream, there's what's added in there. It's called parity bits. Both odd and even parity bits are added to that particular data stream. And then that's what the forward error correction uses to make the corrections. Now, forward error correction, or the FEC, adds those additional data into the particular stream, and then it's able to correct data, or correct the actual constellation itself. Data transmission systems such as high-speed data are not real-time, and it has the ability of resending data. Live video, though, it's not able to resend because it's live, so it has to be close to real time, which is the same with voice over IP. It's also real time, so it doesn't have the ability of resending, but it has what's called a jitter buffer, which at least allows the buffer to put or to correct timing of the symbols or the packets that are received. Now, there's also what's called interleaving. Now, interleaving, a burst of errors can cause more problems with the pictures than errors that are spread out. Now, to minimize the effect of burst errors, a technique known as interleaving is used. Interleaving effectively spreads out burst errors so that they have the least effect on the picture. So data is interleaved by sending 128 symbols from 128 different packets. The next 128 symbols sent are the second symbols from each of the 128 packets, and so on. So you can notice how the packets are now spread out more, or the symbols are sent from the packets that are spread out, and it's a better chance for corrections to be made. Now, we've covered a lot of things. We've talked about different types of tests that can be measured, digital carriers under test, the 64 QAM, 256 QAM, and remembering that that when you're measuring your QAM carriers, that you're looking at the average power measurement of that particular QAM carrier. And we talked about MER, the BER. We talked about pre, post, and true BER is when there's actually a digital board or a digital piece of equipment that's actually measuring every bit that passes by it, opposed to an estimated BER that looks at the MER, and it uses the Reed-Solomon method, and it comes up with what the BER should be. Just remember, when you're looking at an estimated BER, that it's possible for estimated BER to sometimes miss if there's random burst of noise that pops on screen. It can miss some of that information versus true BER. Now, with the 860 DSPI, it has the ability of looking at both. It can look at it from a true BER that analyzes every bit, or an estimated BER that makes an approximate. Making an approximate gives you a quick measurement. It gives you a quick approximation of what type of errors that you're receiving. Digital carriers are more robust than analog carriers. And complex digital modulation schemes sacrifice robustness for throughput. High peak-to-average ratio. Digital signals are set between 6 to 12 dB below analog carriers. And that's assuming that it's 6 megahertz channel spacing. Just remember, and I kind of said this earlier, that analog carriers are measured using a peak method, but digital carriers uses an average method based off of the average power in that 6 megahertz bandwidth. So some of the anomalies of digital versus analog. 43 dB carrier to noise is needed for cable systems to comply with their FC or with the FCC requirements. Most systems usually around 48 to 50. The ratio is video RMS peak level to RMS noise level in that 4 megahertz bandwidth, which is where the noise is measured. Digital data, as was mentioned, is more robust. There's no noise hidden in the service, and it can survive with a much lower ratio. This depends greatly on the type of modulation, adaptive equalization, forward error correction, so on, though. Now, if the analog looks good, will the digital have problems? It very well could. Standing waves, or which are reflections, and group delay all affect digital signals more so than analog signals. At best, with an analog signal, that the picture quality could look pretty good from a noise or distortion standpoint, but in an analog environment, when you have reflections on an image, it would look like a double image, or what we call ghosting out in the field. So the standing waves and the effects of standing waves, analog carriers is really no detrimental effect, other than, like we said, is the trailing edge ghosting. Digital data, though, is a totally different story. You can have group delay issues. And this is why adaptive equalization is incorporated. And most equipment is specified for less than 1 dB per 1 megahertz for adaptive equalization. So the preventative maintenance is when those services are added every day, and the preventative maintenance has to adapt to those services that are being added. Test equipment gives a true representation of the system integrity, and it prevents interference to services being offered. Now, the thing is that with the preventative maintenance, it's important that you stay proactive and not reactive, and you have the tools to do that. You want to know about the problems before the customers do. If the customer has to call you to tell you that there's a problem, then it is too late. It should have been caught before then. So now, one of the things that comes up a lot of times, because remember, I was letting you know that that digital is a haystack, and it's total power across that 6 megahertz bandwidth. But when there's noise that's happening under that QAM carrier, I still want to see it, because I know that those are the things that will potentially knock out my my service. So there is ways to look at noise under the QAM carrier. One of the ways is using error vector spectrum. In the 860 DSPI, it's called EVS, and this allows you to look at noise under that QAM carrier. So if you look at the screen, you see that there's the digital haystack that I've talked to you about in that 6 megahertz span. Now, what happens is that we can't see what's going on under that QAM carrier. As far as we know, there could be noise there, and we may not see it. So what QAM EVS does is it removes that haystack out of the picture digitally. So we have the ability of doing that because we have a digital signal processing, so it can mathematically remove that haystack from the screen, and the only thing that will be remaining is the noise floor that's under that QAM carrier. Okay, now let's just talk about some digital troubleshooting tips that you can take away. Verify that the problem is happening before you troubleshoot. You want to know that the problem is going on because digital or problems can be intermittent. It can come and go. So first, verify that it's happening. So my first step is going to be look at the customer's television. If they're saying that it's tiling, I want to see if it's tiling, when I'm there. And then check your RF levels. Then you want to check your MER, your BER. Look at your constellation patterns. And then just also measure your signal leakage, because we've talked about in our other series for signal leakage that if signal is leaking out, there's a strong chance that signals are going to be leaking in as well. You can check the return spectrum for excessive noise, because that's another thing we talked about in one of our other series was return spectrums. You know, how that area it accumulates a lot of that composite noise that's coming back from the network. So if you have a clean return, then there's a strong chance that your forwards are going to be looking pretty good as well. And then determine what channels are being affected, because remember that you can compress multiple channels on a individual QAM carrier. So if you're having a problem with HBO East, and you know that that on that same QAM carrier that there's HBO West and there's ESPN or whatever else is combined with it, then you want to check those other channels as well, and then that'll point you to, you know, hey, is it an actual problem with that particular QAM carrier, or is it something with maybe just that particular channel that needs to be addressed in the head end? Checking your connectors, making sure your connectors are nice and snug, because that's one of the biggest problems that that I run into when I'm looking in the plant are loose connectors, and that will cause you a lot of problems. Making sure that the wiring is proper, and then verifying what time the problems actually occur. Because different problems, especially when you're talking about ingress and noise, that the problem can happen more at night, or it could happen more during the day. Maybe it's a particular machine shop that's in the neighborhood, and whenever they turn on a particular drill press, maybe that's when they start causing bit errors or having problems on the customer's set when they turn on that piece of equipment. Using the diagnostic screens on your set top. I mean, that's a useful troubleshooting tool, but what you see on the set top, you should be able to look at your meter, and it should agree with each other. So, but if let's say if when you're looking at the plant coming in and everything is nice and clean, but on the set top box itself it's showing errors, it could be a problem with the box. And then looking at any noise that's falling under the QAM carrier. Using the QAM EVS will point you to a lot of problems that you wouldn't typically see. So your digital measurement results, these are just kind of some industry standard as what you're looking for as far as for your MER and your BER. At the tap, you want greater than 28 dB. For your pre's, you want greater than a 1.0 e to the -7. And then for your posts, you always want that to be able to correct any errors. So you always want that greater than a 1.e to the -9. And then you can also see the levels for the set. Now remember, this is the worst case. Now, your system, I'm sure, will have tighter specs or tolerances than this. A rule of thumb that I like to use is for MER, you want it in the 30s. If you see your MER below 30, you have some work that you need to do. For your pre and your for your pre's, you don't want that to drop below a -0.7. If it starts dropping below there, I know that there's some stuff going on that I need to work on further. For your posts, you always want it to make all of the corrections. That's after the forward error correction is kicked in, you want it to be able to correct any errors. So you always want that at a -0.9 or greater. So as a conclusion, home wiring integrity is much more important with digital because of the problems we talked about. Digital levels must be measured with signal level meters optimized for digital carriers, because remember, you're looking at total digital power. Unlike analog channels, that's looking at the peak of the individual carrier or the individual 300 kilohertz measurement that it's looking at. So it's a totally different. You're looking at total digital power or energy across that 6 megahertz bandwidth. Conventional analog test also needs to continue to be conducted to ensure that the integrity of the system for digital on the forward path is going to be successful. So still look at your carrier to noise on your analog channels, your other distortion measurements, whether that's composite triple beat, the CTB, or the CSOs, and so on. And then also your signal leakage and so on. Sweeping the reverse path is necessary to ensure the optimum performance. The thing is that return is an area to where a lot of distortion will gather in that particular area. So you want to make sure that that return stays nice and clean. If you can keep that clean, you'll also notice improvements on your forward. Field ingress testing and head-in ingress monitoring is definitely needed to locate and control ingress, because you want to be able to identify problems before the customer has to call. Remember, you want to be proactive, not reactive. So hopefully there were things that helped you out in this particular webinar series. I know I covered a lot of information. Now remember that this particular and the other webinar series will have links provided on our website that you can go through this again on some of the points that I may have went through a little bit faster. Then you can slow it down and you can go over it and learn more about digital, because that's the direction that the industries are going. Eventually, that's all you're going to see is totally digital systems, and by following some of the things that I mentioned here, you'll be ahead of the curve. Okay, now I'll respond to the questions that were sent. Okay, actually there were quite a few questions that came up, so I want to try to address all of them that came through. One of the questions that was mentioned was referring to the digital broadcasting. The questions with DTV launch for broadcasters utilizing the 8 VSB and 16 VSB modulation, what impact does it have on 256 QAM modulation signals? And then the second part of the question is, what would this 8 VSB signal look like on a spectrum analyzer? The first part of that question, as far as an impact on a 256 QAM, there really won't be an impact, because remember that that you're putting the content on that QAM carrier. So as far as from a troubleshooting standpoint and so on, it's all you're going to troubleshoot that the same. And even from a ingress standpoint, because you're looking at overall power opposed to peak carriers, even that will actually show signs of reduction as well. And then as far as what it looks like on a spectrum analyzer, for if you looked at it with a constellation, how you have the individual grids, for 8 VSB, it's going to look like vertical bars that's on there, and you'll start seeing the kind of a Boeing effect and things of that nature. But the display looks a little bit differently. If you want to send me an email, I can send you some information on the 8 VSB, what it looks like, and how to troubleshoot it. I had a few questions about, is this particular webinar series, is it possible to download it? Yes. Yes, you can actually download this. You can go to our website, and it actually gives it'll provide a link to all of our webinars, and you can download those and get all the information. The next question, does a 256 QAM signal have more power than a 64 QAM. And then with that in mind, in order to reduce the first and second harmonics, does the levels need to be different, 6 dB for 256 and 10 dB for 64 QAM? From a power standpoint, whether it's the 256 or the 64 QAM, it's similar power. So that's not really the issue. The reason that you want the difference of a level between 64 and 256, you want the 256 to run a little bit higher to get it further out of the noise floor because it's more susceptible to interference because of the layers, like what we mentioned in the presentation. So let's see, MPEG-2 transport string contains 188 bytes of data. Does FEC increase the number of bits to the transport stream? No, it doesn't. It doesn't increase the bits, but what happens is because of the contents that's there, you can't carry as many MPEG, you can't carry as much MPEG streams as you would a regular digital signal where you can compress more channels just because of the bandwidth it takes up. Let's see, there was a question about the FCC does not help with live video, so when we troubleshoot video on demand issues, do we focus on the pre-BER? That's always a given. Always focus on the pre, whether it's video on demand or your regular digital, because that's where that actually shows you your actual impairments. So you always want to work off of the pre's. Will a constellation show all possible errors, or are there some problems that may not show up on a constellation? Actually, constellation does have the ability of showing all the errors, but sometimes what you can run into is because of the amount of errors that you may have, that your forward error correction can lose lock, and you actually won't lock in on the signal at all. And you know, and that's if it's bad enough. But as far as the different problems that you have, the constellation should show it in some form or another, even though at times you may not be able to distinguish it as much. To measure true BER, use the BER option, not the QAM option. It's kind of a question. Understand this is referring to on the 860 DSPI. You have a BER option and you have a QAM option. With the QAM option, you can actually show both the hardware method, and you can show using the software method, the Reed-Solomon method. You can use both methods, and it's all set up in your setup menu in order to do that. With the true BER, you'll usually leave that in hardware, but you also have the ability of even changing that as well, so that that you can look at it from using the hardware or using the cable modem. There's a question about can I send the PDF of this particular presentation? Yes, I can. For this presentation, just send me an email and with your email address, and I can send a PDF of it. There was a question about reflections. You know, if I could explain reflections. Understand what reflections are is whenever RF does not see 75 ohms. If it does not see 75 ohms, we talk about that a lot of time with terminations. If it does not see 75 ohms, then signal reflects backwards or upstream on the cable. When that happens, it causes standing waves, or the signal is out of phase with the forward signals, and that's what causes reflections. On analog signals, it's going to be ghosting, the double image. But on digital, it could cause you tiling and things of that nature, and that's the reason that there's the adaptive equalizer in there. Let's see, does the EVS show coherent interference under the QAM or just noise? It's actually going to show whatever's there. You can kind of look at EVS once it removes the digital haystack or the haystack out of there. Whatever you would see on the noise floor as if you looked at it with the spectrum analyzer and that carrier was not there, that's what you're going to see. Let's see, we're just about done. Also, any questions that I don't get a chance to respond to because of time, feel free. You can always email those questions, and then also, as you see on the screen, we have a support forum that we respond to those all of the time. You can actually post questions there, and the entire apps department and engineering department looks at that daily, and we update it. And also, we do have our support email that you can send directly to the applications group, and we can respond to questions at that time as well. So let's see. Let me see. I'm almost there. Measuring. It says, how do you recommend measuring a CNR for a QAM carrier? Usually, when you're looking at a QAM carrier, you're usually going to be you're going to be using your MER to make that measurement. But if you're talking about the composite noise ratio, as if like an SNR or so on, if you have full digital, you would have no place to actually make the measurement for seeing where your noise floor is. You could, in theory, use like the QAM EVS, but usually you're going to use your MER for your measurements for the QAM carrier to look at the quality. Let's see. How does the BER measurement of a trilithic meter compare to the JDSU SDA? Well, I don't want to do a direct comparison. Some of that you'll have to refer to with the SDA or with JDSU. But just understand, with our meter, we look at BER in real time using the hardware. And because of that, we can capture some things that you're not able to capture when you're using the Reed-Solomon method, because the software can burst the information. So beyond that, you'd want to check with JDSU, and they can give you some more information on how the SDA is actually making its measurements. We're almost done. From what value can we consider that the digital image becomes bad? Usually, from looking at it from a BER standpoint, from a cliff, when you're talking about like a cliff effect, that the cliff effect is usually going to start happening when you get to the minus 0.6. Somewhere in that range there, you're going to start seeing it affect the post, and you're going to start seeing more impairments at that time. This question: do you have a more of an entry-level training for on QAM broadcasting? Yes, you can contact me. Send an email, and we can get maybe some training that's a little more geared for entry level and so on. Let's see. We're going to answer a few more questions. Just a few more questions, then we're going to the rest of them that feel free to send those to me. Let me see. Do you think that we can have a level meter for testing and measurement with options as well? Okay, you can reach me offline for that one. Okay, is there a simple method to figure out what the MER should be in relation to the digital level and where the cliff effect is? The only thing I can say to that is that once you start getting when you start getting below 30, that's when you're going to start having problems. And depending on what set-top box that you have and so on, there's different thresholds to where you'll actually have the true cliff effect. It can vary, but just remember, if it's less than 30, then you want to start being prepared that you could start getting a cliff effect. The name of the equipment that digitally removes a haystack is called a QAM EVS, Air Vector Spectrum, and that's on the 860 DSPI. few more questions. The questions are continuing to come in. When using the EVS, the QAM EVS function for a digital channel, if you observe the peak moving around approximately 2 meg around the digital channel frequency, is that a good indication of surrounding signal noise interference? Will the result be bit errors? If you see any type of interference that's under that QAM carrier, that yes, you will start seeing bit errors, and you'll also see impairments with your MER as well, because those bits are going to get pushed further away from that ideal center cluster of dots. If you, my email address is not on there, but the links that are sent out, and there's also some reply stuff that is sent with the actual invitation when you signed up for it, has my email address. But my email address is tholmes, THOLMES @trilithic.com, or you can send email directly to support. To the support email, the support @trilithic.com, which that's on the screen. There's another question about asking, does the 860 DSPI have the 8 VSB mode? Yes, it does. It does have that option. Regarding adaptive equalizer response, who would have this tool? Field techs as opposed to head-end techs? Yes, typically you're going to see that more from the field techs, because they're going to be looking at the reflections that's coming back on the upstream. In the head-end, it's not going to be. You're not going to have, or you should not have issues, that type of issues from a head-end side of when you're looking right off of the combiner or the equipment itself. Is a standing wave problem most likely to affect MER or BER? That's a good question. It could actually, depending on how bad that it is, you could have a problem with both, just because of the fact that since it's not receiving or not able to receive the bits in its proper formation, because of the fact that it's having the reflection, you could have some bit errors, and then also because the bits are not in its proper spot, you can also see the MER. You can see bits pushed away, but usually when it's a standing wave issue, the adaptive equalizer is what's really going to be affected, because that's what's making the corrections. And if the reflections are bad enough, then the adaptive equalizer will be overworked, and it won't be able to make all of the corrections that it needs to. Then the question: where's the adaptive equalizer test? Where should it be performed? In the house, at the tap, at the node? Really, any of the spots you can actually make that measurement, because just remember, when you're looking at the QAM signal, you're looking at the forward signal, and that whatever is coming in that's affecting the adaptive equalizer is what's coming from further downstream from you, coming back upstream. So that's what the reflection is. So any of those spots can actually be a useful tool to use in any of those locations. Let's see. I'm going to answer about 2 or 3 more questions, and then the rest of them, if you have any other questions beyond this, you can go ahead and send them to me. Let's see. Can the pilot module on an RF amp to generate problems, or can it generate problems on digital channels? I'm not sure exactly what that's referring to, because you're your pilot, if I'm understanding the question properly, the pilot, when it's referred to in an amplifier, that's actually what the amplifier is using to make its adjustment, whether it's like with your AGCs or what have you. So it's a receive thing, not necessarily. It's not sending out an actual pilot signal. So, like I said, I may be misunderstanding the question. You can always reach me offline for a little more clarity on that. Let's see, is there a limit to the amount of signal required to accurately measure MER? Well, as long as, and depending on your meter and what the range is of that particular meter, as long as the meter can make the measurement, it's not going to allow you to make a measurement outside of or with a level lower than what the meter is going to be able to interpret properly. So if the meter is displaying the result, then it's giving you it should be giving you an accurate measurement. See, does a QAM EVS function, or is there a QAM EVS function available in an 8 VSB mode? No, it's not. That's a good question, but no, not at this particular time. And then there's a question about the cost of the EVS. Feel free to reach me offline, or your sales rep. They can give you some specific information as far as how much any of the options cost on the 860, or to even respond to if let's say you don't have an 860 DSPI and you're wanting to purchase one, you can always contact your sales rep, or you can send me an email directly, and I can get that information to the proper people, and then they can get you the information that you need. All right, I think that's it, and good to hear from you, Les Reed. All right, if you have any other questions or things like that, feel free to reach me offline, and we can address those. Remember, the support email is support@trilithic.com. If you want to go to our forum page, you can go to the you can see the actual link on the screen there. Follow that. You can also call directly to the sales and application support. That direct number is 1-800-344-2412. All right, well, that's it. I appreciate everybody sticking in. I know there was a lot of information given. Hopefully you're able to take some of it away from you. And like I said earlier, is that if you do have additional questions, or if you need some additional training, or if we even need to set up training for your group or your location, feel free to contact me directly, and I can try to accommodate some additional training groups. All right, thanks a lot. Talk to you soon.